Hello everyone and welcome to today's Explainer. I am absolutely thrilled you're tuning in for this one because today we are going to unlock some of the absolute most powerful tools in all of geometry. Seriously, this is where the training wheels come off. For a long time now, you've probably relied pretty heavily on your basic trigonometric ratios, sine, cosine, and tangent. Good old SOHCAHTOA. And they are fantastic. But there's a massive catch. Those ratios only work when you have a neat, tidy, perfectly formed right-angled triangle. But let's be real for a second. The real world, the complex questions you're going to face, they're rarely that neat. So today, our ultimate goal is to break right through that right angle barrier. We are going to learn exactly how to solve any triangle we encounter, no matter how weird or skewed its shape might be. We're stepping out of the basics and into advanced territory. Grab your calculators, because this is going to be a game changer.
Okay, let's take a quick look at our roadmap for this session. We'll start by looking conceptually beyond those right-angled triangles. Then, we'll break down the sine rule step by step. After that, we're going to explore a very sneaky hidden trap called the ambiguous case. You absolutely need to know this one. Then, we'll master the cosine rule, and finally, we'll test all these new tools against some real-world application problems. Let's get straight into it.
Section 1. Beyond right-angled triangles. Let's define the primary obstacle we are tackling today.
Okay, I want you to imagine you're looking at a triangle. But there are no 90-degree corners. None. Just 3 random intersecting lines creating 3 random angles and 3 sides. How do you find a missing length? Think about it. Your basic opposite over hypotenuse suddenly completely falls short. Why? Because without a strict right angle, there is no true hypotenuse. The hypotenuse is, by definition, the side opposite the 90-degree angle. So it creates this real intellectual tension, doesn't it? We have this vast mathematical world, but our basic foundational tools are suddenly useless. We need a bridge. We need a new set of rules that connect what we already know to what we don't. And before we continue and build that bridge together, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, moving into Section 2, the sine rule explained. This is that exact bridge we were just talking about. This is our first major tool to completely break the right angle barrier.
I want to walk through how this formula is actually built because it's not just magic. It's a truly beautiful piece of logical problem solving. Imagine a standard non-right angle triangle. We'll label the corners capital A, capital B, and capital C. Now, what if we draw a perfectly straight vertical line right down the middle, from the top corner directly to the base? We'll call that new height line H. Take a second to think about what we just did. By dropping that perpendicular line, we effectively forced 2 smaller right-angled triangles to exist back-to-back inside our original triangle. Now we can use our basic SOHCAHTOA again. Looking just at the left side triangle, the sine of angle A equals the opposite side, which is our new line H, divided by the hypotenuse of that little triangle, which is side B. If we rearrange that, simply by multiplying both sides by B, we get H equals B times the sine of A. Now, do the exact same thing on the right side triangle. H equals A times the sine of B. Here is the brilliant part. Since that vertical altitude line H is the exact same line for both of our new equations, we can just smash the 2 equations together. If they both equal H, they must equal each other. So B times sine A equals A times sine B. With a really quick bit of algebra, just dividing both sides to clean things up, we arrive at a perfectly balanced, beautiful formula. Lowercase a over the sine of capital A equals lowercase b over the sine of capital B. 2 right-angled triangles basically join forces to solve a non-right-angled problem. It's mathematical teamwork.
Now, what's really interesting about this rule is how incredibly flexible it is. On the left, you're seeing the standard formula exactly as we just derived it. This version is absolutely perfect if you are trying to calculate a missing side length. The unknown side is already on top of the fraction, making it super easy to isolate. But look at the version on the right. Notice what we did? We just took the reciprocal. We literally flipped the fractions upside down on both sides. Mathematically, it's the exact same relationship. But practically, if you're trying to find a missing angle, using this flipped version where the angle is on the top makes your algebraic rearrangement significantly easier. You don't have to deal with getting your unknown out of the denominator. You just multiply the bottom number across to the other side, do your inverse sign, and you're essentially done. It's a massive time saver when you're under pressure.
Section 3. The ambiguous case trap. Now, as incredibly powerful as the sine rule is, it hides a dark secret. A trap that catches so many students entirely off guard.
I want you to look really closely at the numbers here. If you grab your calculator right now and type in the sine of 30 degrees, it's going to spit out exactly 0.5. But If you clear that out and type the sine of 150 degrees, it also equals 0.5. The sine of 60 degrees is 0.866, and guess what? So is the sine of 120 degrees. Why on earth does this happen? It's all because of the natural symmetry of the sine graph. If you picture the sine wave, it starts at 0, it curves up to peak perfectly at 90 degrees, and then it drops back down, perfectly mirroring itself until it hits 0 again at 180 degrees. So, why does this matter for solving triangles? Well, imagine you're using the sine rule to calculate an unknown angle. You punch the numbers in, hit inverse sine, and your calculator spits out, say, 69.8 degrees. Your calculator is programmed by default to give you the acute angle, the one less than 90. But what if the physical triangle you are actually measuring happens to have an obtuse angle, an angle wider than 90? Because of that mathematical mirror effect we just talked about, an angle of 110.2 degrees produces the exact same decimal ratio. Your calculator is literally hiding a second valid angle from you. It has a blind spot. Stop scrolling, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, back to the trap. The crucial point you need to remember is this. If a problem gives you an angle and two sides and it doesn't explicitly tell you whether the triangle is acute or obtuse, you have to be highly suspicious. You must take the acute angle your calculator gives you and subtract it from 180 degrees. You have to manually check for that hidden obtuse angle. If that second, larger angle can physically still fit inside a triangle along with the other angle you were originally given, meaning they don't add up to more than 180 degrees together, then you have what's called the ambiguous case. You literally have two entirely different mathematically correct triangles that can be drawn from the exact same starting information. Always check for this hidden second triangle.
Section 4. Mastering the cosine rule. Now the sine rule is fantastic, but if you've been paying close attention, you'll notice it requires you to know a matching pair. You need to know an angle and its exact opposite side to make the formula work. But what if you don't have a matching pair? That is exactly when we bring out our ultimate heavy-duty geometry tool.
Once again, to figure out where this comes from, we drop a vertical line, h, down the middle of a random triangle to make two right-angled triangles. But this time, instead of using basic sine ratios, we apply Pythagoras' theorem. Good old a squared plus b squared equals c squared. And honestly, this brilliantly illustrates how Pythagoras actually evolves into the cosine rule. We set up a squared equation for both the left inner triangle and the right inner triangle. When we equate them, again to eliminate that imaginary h-line we drew, and then we expand the brackets, we get something that starts looking really familiar. We get a squared equals b squared plus c squared, minus 2cx. Finally, we substitute that little x using basic cosine logic from the smaller triangle, which gives us the final glorious masterpiece. A squared equals b squared plus c squared minus 2bc times the cosine of angle A. Just look at the very beginning of that formula. A squared equals b squared plus c squared. It literally is Pythagoras. The entire back half of the equation, the minus 2bc cos A part, is just a mathematical adjustment factor. It's compensating for the fact that the angle isn't exactly 90 degrees anymore. If the angle was 90 degrees, the cosine of 90 is 0, that whole back half vanishes, and you're left with perfectly normal Pythagoras. It's completely mind-blowing when you realize it's all connected like that.
And just like we did with the sine rule, we can manipulate this formula to serve different purposes. The left side shows the standard form. This is your absolute go-to when you know two sides of a triangle and the angle squeezed right between them and you want to find the length of the opposite side. But if you rearrange the equation using algebra to move terms across the equal sign and isolate the angle, you get the version on the right. Cosine of A equals b squared plus c squared minus a squared, all divided by 2bc. This rearranged version unlocks an incredible superpower. Think about it. If you know the lengths of all three sides of a triangle, just 3 lengths of sticks lying on the ground, you can use this formula to find exactly what interior angles they form. No right angles required, no known angles required at all to start. Just 3 sides and you can unlock the whole shape.
Section 5. Real-world applications. Let's move out of the theoretical and see exactly how these rules apply to real-world scenarios from our source material. Because listen, these aren't just abstract formulas meant to torture you on an exam paper. They actively map the physical world around us.
Okay, picture this in your head. 3 yachts, let's call them A, B, and C. They are intensely racing off the Cape, out in the open ocean. You have radar, or a rangefinder, and you know the direct distance from yacht A to yacht B is 220 meters. From yacht A to yacht C is 450 meters, and from your exact vantage point standing on yacht A, the angle between those other 2 boats is 55 degrees. The question is,
How far apart are yachts B and C out there on the water? Look at what you have. You have two sides and the included angle squeezed between them. You do not have a matching pair of an angle and an opposite side, so the sine rule is out. This is a perfect textbook job for the standard cosine rule. You just plug your known numbers into the formula, calculate the squares, apply the cosine of 55 degrees, do the subtraction, and finally take the square root. And just like that, sitting on your boat, you have precisely calculated a massive, physically unmeasurable distance right over the ocean waves.
It gets even more interesting when we start looking at more complex systems. Imagine 4 rugby players, W, X, Y, and Z, scattered dynamically across a pitch. Together, their positions form a 4-sided shape, a quadrilateral. And you're told the distances between various players are 20, 24, 30, and 40 meters. And maybe you only know one single angle in that whole shape, say 80 degrees. Now, you can't just solve a weird 4-sided shape with one quick formula. It doesn't work that way. But if you imagine drawing a straight diagonal line between 2 opposite players, what do? You instantly split the pitch into 2 separate triangles. Now you're in business. You can use the cosine rule on the first triangle to find the length of that new diagonal distance you just drew. Once you have that new diagonal length, you essentially have the key to unlock the second triangle. You can jump the border into the other triangle and start using the sine rule to find the remaining unknown angles or sides over there. Chaining these rules together is exactly how we completely decode complex multi-triangle environments. It turns an impossible polygon into a simple step-by-step puzzle.
So to wrap our heads around absolutely everything we've covered today, here is your definitive, foolproof heuristic toolkit. When you're sitting there looking at a geometry problem, just pause and ask yourself exactly what information you have in front of you. First question, is there a right angle? If yes, keep it simple. Do not overcomplicate it. Use your basic SOHCAHTOA. No right angles? Okay, look for a matching pair. Do you have a known side and its exact opposite known angle? Got that? Boom, use the sine rule. It's fast and easy. What if you are given all 3 side lengths and you need to find an angle? That's when you grab the rearranged cosine rule. Are you given 2 sides and the angle squished directly between them? Hit it with the standard cosine rule to find that third side. And finally, remember the absolute golden rule. If you ever use the sine rule to find an unknown angle, always check for the ambiguous case by subtracting your answer from 180. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.
We've seen today how to measure distances between racing yachts, how to map out the exact positions of rugby players on a field, and honestly, you could even use these exact same rules to find the distance between 2 trees standing across an impassable raging river, all just by measuring a couple of angles and a baseline from dry land. Mathematics literally gives you the power to throw an invisible, perfectly accurate measuring tape across any void. So I'm going to leave you with this final thought. What other invisible barriers in science, in engineering, or even just in everyday life can this geometry help you cross? Keep practicing these rules, keep looking for those hidden triangles in the world around you, and I will see you in the next explainer.